Tuomas Koskela from UCL here today, who's going to talk to us a bit about reproducible benchmarking and some of the work he's been doing with that.
Okay, thank you for the introduction and thank you for inviting me to talk here today. So yeah, my name is Tuomas. I'm a senior RC at UCL. We have quite a big central RC team in UCL, about I think 50 people by now. And this is some work we've been doing with ExCALIBUR hardware enabling software, which is one of the enabling software projects they have funded. And yeah, the idea is to build a portable benchmarking framework that we can use for both investigating new hardware and testing new software. So the motivation for this work comes really from the idea that like synthetic benchmarks like Stream and Limpack are fine for checking that the vendor is not lying to you when they're selling you software and telling you how much it can do, but what we really want is to know how well new hardware can run our applications, and for that really the only way is to run the applications and test it. And as we all know, for Exascale and things that come after Exascale, we are dealing with more and more diverse hardware. So, for example, the US Exascale program, I think, is now split between NVIDIA, AMD, and Intel GPUs on their 3 flagship systems. And basically, if you want to program for them, you need 3 different programming models or one that compiles on all of them. So yeah, so applications that want to be successful in the future have to be performance portable. So basically written in a way that you can run it on diverse systems. And as RCs, I probably don't have to tell you this, but transparency and reproducibility are really, really important. So if you've benchmarked an application and got a result, how do you communicate that to others? How do you tell, how did I get this result? What do you need to do to reproduce this result on your system? So the kind of way I've come across people doing benchmarking, so you get some new hardware, maybe like your organization may maintain a set of benchmarks that you always use. If you don't, there's a lot of benchmark suites. You can go online and find one that suits you. You need to find people who know how to port these benchmarks into the new system, basically. And this may be fine if you've got permanent staff, and less fine if you're relying on postdocs that leave every couple of years. So you need to get these people, get them to build their benchmarks, get them to run their benchmarks, and report the results back to you. And this involves a lot of sort of manual labor. It involves a lot of sort of knowledge hidden in people's heads that you might find difficult to retrieve. So that's kind of the yeah. If you're buying a new system, that's kind of what might be the workflow that you do to evaluate that system. I've got another example from here. So this is from Tom Deakin from Bristol, who we are working with, and he does research on performance portability, and he does these studies where he has a benchmark called Babel Stream that I'll talk a little bit later about, and they write it in every conceivable programming model they can get their hands on, and then they run it on every conceivable architecture they can think of, and collect a performance number basically, and then they generate this kind of tables to see how performance portable different programming models are. And why I'm showing this example is that he and his team, to generate this graph, took them about 3 months of work, to just after writing all of those benchmarks to build and run them on each one of these. I think there's like maybe 60 combinations in this table, and that is a lot of effort that as RSCs we would like to automate and make more accessible to users who are not researchers specializing in this kind of work. So we started with some funding that got diverted from a different ExCALIBUR project, thinking about what might an automated benchmarking framework look like. So this is a slide that Todd Gamlin from Lawrence Livermore was presenting in supercomputing last year, and I especially like this middle bit here where he said pieces to build a benchmark suite are something like this. Use Spack for builds, use ReFrame for runs, some generic format specification to tie it all together, and public cloud infrastructure to keep it running. Well, we're not doing the public cloud bit, but all of these other things are basically exactly what we were thinking of using. So some of you might be very familiar with Spack. I apologize. I'm going to spend just a little bit talking about Spack and ReFrame. So those are the main two building blocks that we are using, and we're not really doing anything new here. We're just like making them fit together. So Spack, for those of you who are not familiar with it, is a package manager. It like manages dependencies and automates building software. So it's not a replacement for a build system like CMake or other tools. It will call your build system after it has worked out the tree of dependencies that your software needs and build all of that. It's developed by the US National Labs, which is maybe not surprising that Lawrence Livermore will advocate it, but the Exascale computing project uses it very heavily, and they have spent a lot of resources thinking about this stuff. So I think that's a decent example to follow. So they support a variety of build systems, and they have a very big repository of build recipes. So most common dependencies you can just build with Spack using their recipes. You don't have to do anything about them. And if I don't want to make this sound too easy, but if your build system is sane, then writing your own Spack recipe is not that difficult. You just specify dependencies and then tell Spack what to build it with. I wasn't planning on going very deep into Spack recipes unless someone really wants to see them. But yeah, it has so you describe everything in Python. It's fairly flexible, and one strong point that I like is very easy to install and run with user permissions. So you can just log into a system, clone Spack, run a setup script, and build stuff. One sort of annoying thing about Spack is that because the repository is part of the Spack Git repo, so when you clone Spack, when you get a version of Spack, you get a version of the repository, and if you want something that has been updated, you need the most up-to-date version of Spack, which means often when you look for Spack on a system, it doesn't have the stuff you want, and you end up building your own. But like I said, it's not too difficult. I'll probably show that in a little while.
Do you have any experience of feeding back and sending packages back to Spack?
Some.
Because I found that very frustrating as well.
Oh.
It's slow, very slow. I mean, it's just slow.
Wait, what's slow? Sorry.
Just contributing to Spack because they have so many pull requests and it just takes ages to do.
Right.
Yeah, we do have some. So we have one of our team members knows some of the Spack developers, and he's been able to get our pull requests reviewed.
Okay, I know who to ask next time.
You know who I mean, yeah, through some other common projects. Yeah, so I think we've only upstreamed one package to Spack so far. That one did not take a huge amount of time. Yeah, but you can also, like, you don't have to get your packages upstream to Spack in order to build them. Like, you can maintain your own recipes, which we do some as well, at least for the time being. ReFrame is a framework for, I think the original use case of ReFrame is for running regression tests on HPC systems, but you can also repurpose it for sort of any sort of general benchmarking. It's developed in ETH Zurich, and I think one of the main developers moved to NVIDIA recently, but they're still very involved in it.
When you say regression tests, do you mainly mean like performance regression tests?
Yes, so I think like the original use case of ReFrame was like automating running the same test over and over again on like some schedule and like keeping track of the history, and it does that very well.
And also a lot of regression performance in some way, but one of the motivation was whenever you update your software stuff on the cluster, you want to check that API runs and things like that. So
Yeah, well, I guess it felt pretty early.
yeah, but you don't want to expose users.
Or you want to, yeah, and you want to see that the performance hasn't degraded.
So that your combinator still works.
Well, you mean like works as in like
Yes, they are able to
compiles.
They are able to compile the code which is able to run.
Okay, sure, but I mean that you can do with any sort of CI system, right?
Yeah,
but
probably what I mean, if you want to check it on the cluster, you need to submit it to the queue.
that is true. Yeah, so that's one of the advantages of ReFrame, that it sort of abstracts away the like the queuing systems, schedulers, also build systems to some degree. So you can sort of describe your application. The ReFrame also has a Python interface. So you write a Python class, there's a few steps you have to define, and then ReFrame internally knows how to generate the build scripts and job scripts for the scheduler, how to launch the job, how to collect the output, so on. So it's very tailored for HPC systems, which is a good thing. And you can sort of separate like functionality of your application from the low-level implementation, which is what we like, because then we can configure ReFrame on a system, and then we can just set up a lot of applications that rely on that configuration, and then we can take the applications to another system where we've configured ReFrame, and it works, hopefully. So I'll show some examples later. And yeah, it has some nice features, so you can sort of parameterize and tag different parts of your tests. You can easily run like parameter scans, like say scaling tests, for example. Just say like run this benchmark over these different combinations of MPI tasks and ReFrame, and also it submits all the jobs to the queue and comes back with the results. So that is quite convenient for running. You can also install it, like it installs with pip nowadays, which is nice, makes our installs a bit simpler. So that's it. So I wanted to talk about what our project, so yeah, I should have mentioned, so we started this project, well, we've been working on this for a while, but we got some new funding and we officially started this project a couple of months ago, so all of this is very much work in progress. I wanted to show what is in the repo at the moment. So we like I said, we need to configure Spack and ReFrame once per system, and then all of our applications can use that. And then we have to describe our applications to ReFrame, and then we've done a lot of work on documentation and packaging. So I think like rather than showing slides, it's maybe easier to just jump here. Does this look okay? The repository looks like this. there's a README that tells you sort of basic stuff about getting started and setting up. There's a contributing document, which is useful if you're looking to contribute new things. We're very much trying to get people involved in this, so we're not really trying to say these are the applications you should benchmark systems with. Rather, we want to provide a platform where people can put the benchmarks that are important for science and then make those portable across systems. I wanted to show how the configuration looks like. So there's like 2 bits in the configuration. Configuration for ReFrame, which basically tells ReFrame how to talk to the scheduler. And if I go to the CSD3 configuration, so this is a Python dictionary, and it just describes the system. It tries to auto-detect the system from the login node names, which sometimes works, sometimes doesn't, depends on how uniquely your login nodes are named. And then you define partitions, which is like different things you can run on. You may notice that we only have a CPU partition here. We haven't put the GPUs of CSD3 in yet. Feel free to open a pull request if you would like them. But yeah, so you say, okay, the scheduler is Slurm, the launcher is MPI run. This is how you access it. These are the sides of the nodes which you want to know for some benchmarks that want to like scale up to the full node, for example. Then Spack works through environments. So one of the problems with Spack is it will figure out all the dependencies of your application, starting from the compiler and CMake and MPI and so on, and it will happily build all of them, and it will take some time. So what we do is we set up Spack environments for the systems we are running on, and in a Spack environment you define the software that you want to use that is already installed on the system. So for example, compilers and other packages like CMake here, HDF5, MKL, MPI, so on. So this is kind of the extra price you have to pay when you start using these tools, is you have to set up all this configuration. It's like in the simplest case, I'll show you later how to do it on my local machine, because there it's fairly simple. But yeah, so once this setting up is done, you can move on and run applications. So I think that is the configuration part. Yeah, so ReFrame supports these programming environments where you can tell ReFrame what the compiler is, and ReFrame will compile your code. We don't do that. We just tell ReFrame to use Spack, and then all the dependency information and like compilers, compiler versions, MPI versions get passed through Spack. Just something to be aware of. The applications. So we got a list of things we or our collaborations have already put in. This is by no means complete or something we particularly encourage. Our approach has kind of been to just accept everything people want to put in, and then you can later like put labels, create suites of benchmarks for different purposes. So I think some of these are from our UCL, the sort of applications that our UCL research computing uses for benchmarking. Some are from DRAC procurement benchmarks, some are just the applications we work with. There's, like you may notice, there's a few sort of synthetic benchmarks like IMB and HPL, but most of these tend to be like scientific applications. So we have an example with Sombrero that kind of demonstrates the structure of the application. So we don't keep any code here. So all we have in each application is a Python file that has the classes ReFrame needs to run the job, and Spack will pull the code and compile it, like preferably from GitHub, but there's other ways you can use. So you define a class that ReFrame will use to run your benchmark. We have a base class called Spack test that has like most of the boilerplate stuff we don't want to repeat. You define things like where can this run, what programming environments this can run in, which should be just default because we don't use them. We give the Spack spec, so this is how we want Spack to build it. In this case, we just want the application Sombrero at a particular version, and we let Spack use whatever is the default compiler. You can set this on the command line when you call ReFrame if you want to do special things. Then you set things like the things you usually expect to set in a job script, like number of tasks per node, executable options, time limit, so on. There is this section reference that you can set if you find it useful, so you can sort of set reference performance numbers for different systems, and ReFrame will, and you can set tolerances. So on Archer 2 we expect 1.2 gigaflops plus minus 20%, I think. And then if the performance is different from that, ReFrame will flag it up and give you an error and say, we've got an unexpected performance, which is good if you're doing regression, and less useful for other things. So ReFrame runs through a few steps, which I think should be, okay. So it runs through like a setup, build, run, sanity steps, and you can tag things you want to happen after or before those steps, so you can customize quite a lot of how the workflow runs. Here we just set OMP num threads as an environment variable, and environment variables get recorded in the logs later. There's a sanity step which basically checks that the program ran as expected. So you typically check something in the output is there. And then there's a performance step where you, parse what is your performance number from the output. So yeah, this is something I should mention. So we're not currently measuring anything. We are relying on the applications to measure their own performance and report it back when they run. That's something I would kind of like to change, but like having a portable profiler is more difficult than I thought, so I'm not sure if that's gonna happen because of like different permissions on different systems. So at the moment we expect the application returns a figure of merit that we just collect with ReFrame and record in our log files. Okay, so that's basically how our applications look. There's a couple of benchmarks we are developing ourselves, but mostly we are looking for people to port the benchmarks they find important into this framework. If you're interested, come talk to me after and we can figure out how to do it, or possibly even how to get someone to pay for it. So very quickly getting started, I'll demo this after I'm done with the slides, but everything except Spack installs with pip, so that's quite nice. You just like create a Python environment, you pip install, all the dependencies of the framework come down. You need to provide your own Spack installation because Spack doesn't install from PyPy at the moment. If you're working on a system like CSD3 where the configuration already exists in the repo, that's basically it. Then you can just run applications, running it on a machine like your own laptop or your own cluster. You need to set up the Spack environment, which has a few more steps, but I'll show that in a minute. Yeah, finally, I want to mention about the things we are working on at the moment. So one thing we want to provide up to some point is post-processing tools, so that you can easily sort of get some visualization out of your benchmarks. And then we're working on a couple of benchmarks that we think are particularly interesting, and then providing some training to potential users. So the post-processing is not enormously complicated. So like I showed in the example, ReFrame parses the output of the application for a performance figure or figures, and it appends it. It has a log file for each application parameter combination, and it just keeps appending that log file with whenever you run the application again, and write some metadata into it, like the time and the spec and environment variables. And we're trying to make it complete enough so that you can reproduce any particular result later. We just yesterday finished the first bit, which was just parsing those log files into pandas data frames in Python. That works now. And then the next step is to kind of pass these to a plotting library. And we're expecting to provide something simple, and then users with special use cases can extend this however they want. The use cases we are kind of thinking of is scaling or other parametric scans. So you may want to run your application on a system and scan over parameters, which may be MPI ranks or maybe compilers or maybe input options or whatever. So we're going to provide something that can plot these, like kind of in some kind of line graphs, like the one on the top. Then regression tests, like I talked earlier. So you may want to have this as part of a CI workflow that just runs whenever you update your code, or runs nightly or whatever, and updates a plot somewhere. So I think this is actually from the Phoenix repo, where you have something like this already running. And then the third thing is the one I showed in the beginning for performance portability. So running benchmarks on different systems with different compilers and collecting this data into some kind of sensible format. I want to mention, I'm not sure if you have worked with this already, but John Pennycook at Intel has this project with Tom Deakin for a performance portability, productivity, performance library, which is like an analysis tool for describing performance portability. And they've written a few papers, and they got a open Git repo. It basically, it says simplest way to work with the library is to collect and store data in a compatible format. So they don't give you any tools to collect the data, which is what we are doing, but we're kind of quite interested in then using this as a front end for our data. I don't think I'm gonna go to the repo. yeah, so then, okay, I said I would talk a little bit about BabelStream. So BabelStream is one of the benchmarks we are interested in porting to the repo, because this will sort of allow us to demonstrate the usefulness of this thing, because it runs absolutely anywhere. So then we can sort of deploy the framework and run one benchmark on a lot of different systems, and hopefully demonstrate that it works, and it works quickly, it's productive, you don't need to waste a lot of time faffing with build systems and schedulers. So this is a very simple benchmark. This is basically the stream benchmark with some modifications. So it should just measure your memory bandwidth and tell you how close you got to what the vendor is telling you. It does the stream vector operations, copy, multiply, add, triad, and dot product. What the special thing about BabelStream is, like I said, it's written in most conceivable parallel programming models, and you can compile it with a lot of different compilers. So it's nice for testing programming paradigms. Okay, I'm not gonna go into a lot of detail. So basically, we've created a Spack package, and this is the package we've managed to upstream to Spack. So in this package, this is a bit of a special case, because we use a lot. So it uses a lot of variants. So you can say like install BabelStream using the SQL 2020 variant and compile it with one API, or compile it with kubectl, or compile it with whatever SQL compiler, and it gives you access to all this whole table of different programming models. So that works fine. It doesn't have any difference in performance to their own CMake build systems, so that's fine. And then the ReFrame package, the pull request is still open. We're still working out ways to sort of expose all of this to the user. So you may notice you need quite a bit of command line magic to get what you want. That may just stay that way because it has a lot of customization compared to your usual benchmarks. So you will need to know something about how to run that. The other thing we're working on, and this is with the Met Office, they are interested in a conjugate gradient solver benchmark based on HPCG, which we think would be useful for a lot of sort of groups doing computing, and the idea is to sort of make it customizable for different types of problems, so different types of A, basically. The Met Office people are interested in a matrix-free version, and that runs on unstructured grids, because their weather forecasting models run on unstructured grids. They're working on implementing this and putting this through Spack. I think the Spack implementation there is also done, and we're working on the ReFrame bits. Yeah, so that's ongoing, and David Case from Reading has been leading on that. Finally, training. So I admit getting started with Spack and ReFrame has a bit of a learning curve compared to just to manually building software using CMake. We want to make this useful to people. That's the main thing. We don't really do benchmarking in our group that much, so we want to produce something that is useful for people who actually need it. So we're trying to improve documentation, and we're doing some training events. So we've got a workshop in RCCon in September. There's very strong rumors that there's going to be a ExCALIBUR program event in October. I'm hoping to do something there. Other than that, I would like to get some feedback. So if you could go to this link, and there should be a quiz there that I may need to activate. Okay, I'll leave that on for a minute. There you go. Does that work? I'll present. So this is just to ask people what kind of training would work best. We've done some. We did a workshop some time ago where we invited a few people for a sort of hackathon type event to just try to build applications with Spack. I think it had mixed results. We didn't really get a lot of things done. Some people have been happy just sort of going through our documentation and coming back with questions. That's fine if people are happy to do that. That's easy for us. Yeah, I would just like to get an idea of what would be the most useful thing for us to do. If you have comments now, I'm happy to answer.
So it's kind of nice talk. But the point which kind of I find the most difficult to deal with is the post-processing. I think it's one that you haven't really gotten to dealing with in a huge way, because you end up with this data set which is so extremely multi-dimensional, and I want to be able to query it in lots of different planes, basically. And
True.
Doing that in a nice way through a web interface or something, it would be nice to have something to do that really.
That is, yeah. So that's kind of what we are planning. So we've got like a plan in place of how to do that, and getting it into these data frames is the first bit. Then I think, you're gonna have to, because there's gonna be a lot of different use cases. So I think our approach is just to give as much flexibility to the user as we can. So just have menus where you select which fields you want to filter from the data frame, basically.
Yeah, and then that's what I'd like to see. It's like when you can go on, I forget which one, the world in data or something, you can select, I want to plot, life expectancy against healthcare or something like that. Yeah. You can just click whichever one. Yeah,
exactly. Yeah, so I think that's something like that we are definitely going to do.
For us, the problem is that I can't be bothered to learn any JavaScript. So.
We've got someone who knows JavaScript. This is really not my area of expertise, like producing websites, so I can't give you very detailed answers, but there's a few technologies. I mean, as far as I know, there's a few technologies that will write the JavaScript for you. You just write Python and the JavaScript gets generated, and we have people who have worked with this type of things.
Looking forward to hearing it.
So maybe, I hope by September we have something we can show in the workshop about the post-processing. I accept that it's still quite early stage. Yes?
Okay, two questions. The first is, do you have to build, for a benchmark application, does it have to be a Spack package?
Not necessarily. I mean, you can. So
you write a Python script that essentially, well, I guess it's more happy, right? And a Spack package is the nice way to do it.
Yeah, so I think.
But given the issues that Chris mentioned,
but you can write your own Spack package very easily.
So you don't have to upstream to Spack. Okay. Sorry, I didn't mention that, but yeah. So we have a repo here in Spack where we have a number of packages that people have written but haven't been upstream to Spack for whatever reasons. Like some of these are not entirely sustainable, maybe, but you can, so you can have a local Spack recipe. That's not a problem. And you can also, like in ReFrame, sorry, let me go to the app. I'm not sure, we may have removed the applications that used to do this, but I think there's something somewhere here, it should say that Spack is the build system. Okay, it's probably been moved to the base class, but basically, so you can say, instead of saying build this with Spack, you can say like expect you have an application, like a executable basically. So don't build it, we will provide the executable, or like,
Okay.
I mean, ReFrame would allow you to build it like with, just call it by calling the compiler. We try not to do that because that gets hacky, but yeah, there is ways around it if you absolutely don't want to build with Spack, but
the local Spack recipes, I think.
Local Spack recipes make it a bit easier.
The other one was, so you had some envisioned use cases.
Yeah.
Do you have explicit examples of groups or systems where they are running these benchmarks, like automatically or on a schedule or something like that?
Well, I mean, I think Chris has an example.
I don't think we're running, not this one, no, we're running our own one, which is based on ReFrame. It would be nice to use this one.
Yeah, so I've been talking to Matt about porting them to this one, and that would be interesting.
You also mentioned Dirac, something about Dirac wanting to...
Yes, so I mean, Dirac, I think, is interested in using this for procurements, basically. So I think there's a few, like Ramses, SVNG, and Trove are codes that they used in the previous round of procurement, and they would like to make the workflow more automatic. So we've worked with a couple of RCs from Leicester on porting their benchmarks. Yeah.
Thanks.
Okay. Okay. So I talked for a lot longer than I thought I would. I was gonna, since I have 10 minutes, I can do a quick demo of how to set this all up, so that this is not just, you don't have to take my word for it, unless people have more questions.
Yeah, no questions on mine.
Okay.
More questions after you've shown the demo.
After my demo goes horribly wrong, I'm sure there's more questions. Okay. So I'm just gonna start from scratch, and the first thing I need to do is I'm gonna just have a Python environment where I'm installing everything, and then I need to clone a couple of things, which I did have notes for, but here we go. So, okay. So like I said in the getting started bit, we need Spack, and then we need our repo. Did I actually show you where our repo is? I showed that in the end. Okay, yeah, good. I thought you might have faster to roam here. I'm glad I was right. Okay, so then once you've cloned Spack, they just, there's a setup script, setup and let you run, and then Spack is there. Okay, so then we clone, so this is the repo I was showing in the talk. There's one surprisingly large file there that I'm not sure what it is. Okay, and then I'm in the environment, so I should be able to just install it. Like this. And it installs a bunch of dependencies. We don't really depend on a huge amount of things. But that should have installed ReFrame, which it did. So we do need to point the ReFrame to the ReFrame config, which is a bit annoying, but that's just the environment variable. Okay, that's there. And then, so now everything is set up, so I could, ooh, that's very low.
It's on the side of the sort of triangle.
There.
Okay.
If we've got a cable.
How does it know where Spack is?
Sorry.
How does it know where Spack that you deploy? Does it assume that it's in the same?
No, so that's the setup script which I run after cloning it. So that puts all the executables in the path and stuff like that. Right. So now ReFrame and Spack are configured. The thing you need to do, I still need to do, is I don't want it to build MPI. I want it to use the open MPI I have on my system. I don't want it to build Python. I want it to use the Python I have. So I need to do a few extra things to set up a Spack environment, which I think goes like Spack and create -d. Created environment, and then I can activate it. So I'm in my environment, and now I need to populate the environment with stuff I have. Spack provides some tools for this, so I can do Spack compiler find. It should find all my compilers and add them to the environment, and then I can do Spack external find and tell it what else I want. So I want OpenMPI. It went and found my OpenMPI. I want Python. It went and found my Python. Do I want anything else? I think that's fine. So yeah, you can check what's in your config. Like this. Oh, my font is way too big to display this. Interesting. Why is it? Oh no, never mind. Okay, so it's got some stuff in spec.yaml, some stuff in packages.yaml. That's probably fine. Okay, so I'm in that environment, but I think like we need to tell ReFrame to use that environment, which we do with another environment variable called ExCALIBUR Spack env. And now everything should work. So now I should be able to call ReFrame. I tell it what do I want to run. I'm just going to run the sombrero example because it will build and run pretty quickly. And then I just say -r for run. And ooh, it failed. What did I forget to do? Demo spec env no such file or directory, because it is with dashes and not underscores. I'm gonna say I should delete my spec cache and try again. Yay, doing demos is fun. Yeah, so why is it's insisting that my...
I mean, this is absolutely classic, isn't it? When you try and do a demo, a live demo, it's very,
Yeah.
very brave.
Maybe you should just create a symbolic link to that directory.
I can just rename that directory.
Or rename it.
Yeah, so I think like I've done this before. I've had the environment named with underscores, and somewhere somehow it still remembers that. Okay, let's try this.
Oh, it's running.
It is running. So it is. So this test has tasks and CPUs per task parameterized. So it runs 4 combinations, and I think most of this time is spent like Spack figuring out how to build it. So you can kind of see what is going on if another terminal opens. By going to the stage directory, so this is where it gives me outputs.
Is it building all these in parallel?
It shouldn't actually be building, I mean, it shouldn't be building all of these because they're all the same executable. It just has different run options. So it should be building one of them and caching them. But I mean, you can see from my CPU usage that it is doing stuff in parallel.
So just wondering how you prevent it from...
Okay. So we're done. So we run 4 out of 4 test cases. They all passed. And then you can, so we have in perf logs, we get output from all of them, and it looks probably not very helpful. So it just, how do I make this make some sense? Well, it prints like a line of headers, and then it prints a line of values with time, version of reframe, name of benchmark, values of parameters, the environment, the performance value, environment variables, and so on. And so now, okay, this may seem to you like a very complicated way of running a benchmark. I think what I should now be able to do, because I don't think I'm going to have time to do this. I was going to go to CSD3 and do this again, but I think we may be out of time. So I'm just going to run another benchmark. So this is the Intel MPI benchmark suite, which has a lot of different benchmarks, and we've used tags so that we don't have to run all of them at the same time. So I'm just going to run the ping pong benchmark, which should be just 2 ranks talking to each other.
Is tag and a reframe concept?
It's a reframe concept. So when you're writing the reframe class, you can define tags for different classes or.
By default, it runs all of them.
Sorry?
By default, it runs.
By default, it runs everything that's defined in the reframe class.
So you just run this on your laptop, right?
So this is just running on my laptop.
Has it got a submissions?
No, so this doesn't have a scheduler. So this just runs.
Right.
But I mean, so if I had time to go onto CSD3, like it should look exactly the same, except I wouldn't have to faff with the Spack environments because the Spack environment is already there and it picks it up automatically. So in theory, it would look simpler on a remote system.
Assuming there is a Spack installation.
Assuming we've done the Spack environment already. So if you don't have a Spack, okay, so now there you go, another benchmark, built, run, and passed, produced outputs. I hope this was interesting to you.